Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. And today's topic we will see semi-implicit scheme. So in the previous lecture, I have discussed about what is implicit scheme and what is explicit scheme. So let's recall once again basically what is explicit and implicit, and then we will see what is a semi-implicit scheme and how it will maintain the stability of a numerical scheme. We will see in detail. So first, let's see what is explicit scheme. So let me take a 1D diffusion equation. So which is dou u by dou t is equal to alpha dou square u by dou x square. Okay. So let me write in the form of explicit method. So for this term, okay. So we will be writing u of I to the power of n plus 1 minus u of I to the power of n divided by delta t. So this is the index notation what we use. So recalling again, so n is the index for time and I is the index for x coordinate and j is the index for y coordinate and k is the index for z coordinate. Okay, so here the term delta t is nothing but time step. Okay, so which is equal to, so the alpha is some diffusion term into, so for the explicit method, so here we have u of I plus 1 to the power of n minus 2u of I to the power of n plus u of I minus 1 to the power of n divided by delta x square. Okay, so here you see basically, so what we are able to see clearly, so n plus 1 is nothing but the only one unknown term we have. So let us actually see the grid terminology here. Okay, so let us take this as index I. Okay, so and this as I plus 1. Okay, so this will be I minus 1. So let us take this as level n. So this is n plus 1. So same, this will be grid points I minus 1 and this will be grid points I and this will be grid points I plus 1 again. So basically, so n is nothing but the initial time level. So n plus 1 is nothing but the final time level. So n plus 2 is nothing but not in final, this is the next time level. So n plus 2 is nothing but the next time level. Okay, so at each and every time level, how the grid point velocities are changing, we will be seeing actually. So if you see clearly, so what is happening? So the I term and I minus 1 term, I plus 1 term, how it is changing at different levels, we will evaluate. So if you see this equation, let's take this as 1. For this equation 1, so what are the unknown variables? We have known variables is, so we have u of I minus 1 to the power of n. So this is what we have. Okay, and u of I, so this is what we have, and u of I plus 1, so this is what we have. So these three are the known variables, so which are coming from the initial conditions. So once we know what are the values of these variables with the initial conditions, so we will find out, so what is the velocity at the grid point, same grid point location I at next time level, which is n plus 1. Okay, this is what we are doing in explicit method. Okay, so basically this is explicit method. Okay, so in the explicit method, what do we have? So we have only one unknown variable and the remaining all the variables are known parameters. Okay, so the order of accuracy, you can see it is delta x square. So basically this is delta t, first order accurate in time and the second order accurate in space. Okay, basically this is first order accurate in time and second order accurate in space. Okay, so let's see what is implicit scheme. Okay, so let's see what is implicit scheme. Okay, so for the implicit scheme, the same equation we will use. So which is dou u by dou t. So which is equal to alpha into dou square u by dou x square. Okay, so we will again change. Okay, so what happens with respect to time and with respect to position, we will see again. But here we will see in different terminology, which is implicit scheme. Okay, so the time derivative term it's same. So which is u of I to the power of n plus 1 minus u of I to the power of n divided by delta t. So this is what we have is equal to alpha. So dou square u by dou x square. So how do we write dou square u by dou x square? So for the implicit scheme, we write u of I to the power I plus 1 to the power of n plus 1 minus 2 u of I to the power of n plus 1 next plus u of I minus 1 to the power of n plus 1 divided by delta x square. So this is what we have. Okay, so this is equation for implicit scheme. Okay, so let me write down what is equation for explicit here itself. So u of I to the power of n plus 1 minus u of I to the power of n divided by delta t is equal to alpha into, so u of I plus 1 to the power of n minus 2 u of I to the power of n plus u of I minus 1 to the power of n divided by delta x square. So this is for explicit. Okay, so here we can see the difference. So basically the LHS term. So this is the LHS term. So this LHS term, so there is no change in the LHS term. So the left hand side term, so there is no change, but the RHS term you can see the superscripts. So basically here we have for the implicit scheme we have n plus 1, for the explicit scheme we have n. So the major difference between the implicit and explicit here you can see clearly on the RHS term, where it states that so there are more number of unknown variables in the implicit scheme and less number of unknown variables in explicit scheme. So in short way to tell, so in the implicit scheme, so we have only one known variable and remaining all are unknown variables, and for the explicit scheme, so we have only one unknown variable and remaining all are known variables. So basically if you see in a straightforward method, so the explicit scheme is very simple to solve. Why? Because it's a value input and get output, so that is a straightforward process. But here for the implicit scheme, so we have more number of unknown variables, so therefore we have to collect the equations. So whatever the equation we have written here, this is at only index I. Okay, so again I am drawing this grid. So let us take this as I. So this is for n, let's say n plus 1, and this is for n. Okay, so we are calculating so the solution at I. Okay, so for the explicit scheme, what do we take the initial values of these values and get the unknown parameter the next time. But here for the implicit scheme, you can see, so what is happening? So the reverse process actually. So these grid points, so these are the number of unknowns. So here we have only one known variable. Okay, so here we have basically one known variable, these are unknowns. But whereas in the explicit scheme, so we have, these are the known variables, here we have only one unknown. So that is the difference. So for this process, what we have to do is, when we have derived an equation at index I, similarly we have to derive equation at I plus 1, we have to derive equation at I minus 1, So when we derive those equations, we will collect those equations and we will form in the matrix form, which is Ax is equal to B. So in this manner we will arrange. So the A will consist of the coefficients of this in parameters, which is u of I plus 1 and this then. So the x parameters. So let me show you. So basically we will collect in this form Ax is equal to B. So this A will consist of a matrix, so which consists of variables 1, 2, 3, some so variables. So the x will consist of the parameters which are, let's say, u of I plus 1, so u of I, so let us take, and u of I minus 1, so at the different levels actually. So this is what we take, and this B is nothing but so if we have any source terms or the whatever the variables we have, so basically we have only one unknown variables. So this is for n plus 1, so n plus 2, something like that. So the values will vary actually. So this coefficient matrix will size will vary. Accordingly, the column vector size will vary. So this also will vary. So this will be u of I to the power of n, u of I to the power of n plus 1. So on it will vary actually. So what we do is like we will arrange in the form of matrix, and what to get the solution vector for x. So we get A inverse B. So this is what we do for the implicit scheme. Okay, so I think the process for the explicit and implicit scheme is very straightforward and clear. So the major difference between the explicit and implicit is, in the explicit scheme we have only one unknown parameter, and the implicit scheme we have more unknown parameters but only one known parameter. Okay, so that is what we have. So the next task is to see, so what is semi-implicit. So here the word itself you can refer that the semi-implicit, the meaning is half implicit actually. So how do we switch basically to semi-implicit schemes? So what is the general equation? We will see. Okay. So basically, let us take the same equation. So 1D diffusion equation, unsteady. So which is same equation. Okay. So here for the left hand side term, so we have to the power of n plus 1 minus u of I to the power of n divided by delta t. Okay, so which is equal to, so here the switching factor comes into major play. Okay, so theta, okay, into alpha of u of I to the power of I plus 1 to the power of n minus 2 u of I to the power of n plus u of I minus 1 to the power of n divided by delta x square. Okay, so this is one factor. So the other factor plus 1 minus theta into same alpha into, so u of I plus 1 to the power of n plus 1 minus 2 u of I to the power of n plus 1 plus u of I minus 1 to the power of n plus 1 divided by delta x square. Okay, so this is the general equation actually. So this is a generic equation. So where theta is called the switching factor actually. So here we can see basically two things are available. So one is the explicit and another one is implicit. So which one will be implicit? So this thing will be implicit. So why? Because the major thing what we see is like, so these are the unknowns. So you can see from the superscripts. So basically the power, so where the n plus 1. So basically, so this is for the unknown parameter. and this is very straightforward, which is explicit. Why? Because so here we have all the values which are known parameters. Now, what is the meaning of semi-implicit actually? So basically, when we use the switching factor, so basically the cases are theta is equal to 0, theta is equal to half, theta is equal to 1. So these are the cases. So when theta is equal to 0, what happens actually? So when we use theta is equal to 0, what happens? So here when we substitute theta as 0, so the explicit term basically fully vanishes. There is no single term of explicit. So fully vanishing explicit things will happen. Now if we substitute here theta is equal to 0, so this term will be fully implicit. So the equation, the resulting discretized equation will be fully implicit. Okay, so when we take theta is equal to 0, so what is happening? This switching factor. So theta is called the switching factor, so which can switch from one scheme to other scheme. So if we have explicit scheme, it will switch to implicit scheme when we use that switching factor. So theta is equal to 0, so it is fully implicit. Basically, it is fully implicit. So when theta is equal to half, what happens actually? So theta half in the sense, so what we do? So we'll take 1 by 2 of this one. So this 1 minus 1 by 2. So 1 minus 1 by 2 will be again 1 by 2 half. So basically, so when theta is equal to half, what is happening? So it will be semi-implicit method. So semi-implicit method in the sense half implicit, half explicit actually. So when do we use this actually, the semi-implicit method? So initially, so when we want to calculate the values for the unknown initial conditions, so we will guess the values. So we don't know what is the initial values of K, which is turbulent kinetic energy, epsilon. Okay, so K, epsilon, alpha T, and so basically the diffusion parameter. Next, the nu T, so which is the viscosity, turbulent viscosity. So these values, if you don't know, so initially when we are doing the simulations, so these turbulence parameters, K is nothing but turbulent kinetic energy. So K is nothing but the turbulent kinetic energy. Epsilon is nothing but the emissivity, and alpha T is nothing but the diffusivity actually, and the nu T is nothing but the eddy viscosity, or the turbulent viscosity. So here, what is happening actually? When we are performing a simulation using turbulence models, so let's say K epsilon, so we need to know what is the initial values of these variables K epsilon, alpha T, and nu T. So if we are not able to guess it, or if we are not able to calculate it, so the one initial step to find out these values is to perform initially explicitly. Explicitly in the sense, initially you will guess the values. After guessing the values, you will get the values of K, alpha T, epsilon, and nu T. So once we get these values, so we will check with the implicit scheme. So when we are doing the switching factor half semi-implicit, so half explicit will be done and half implicit will be done. So for the half implicit thing, so initially we will switch the values of the K, alpha T, epsilon, nu T with the initial conditions. And once we get those values, we will substitute in the implicit scheme such that we will correct it and reiterate it again actually. So this is what we do. Okay. So this is one generic process which I am explaining for the semi-implicit. So there are other numeric or other detailed explanations, but this is the generic way to explain about semi-implicit method. Okay, so when theta is equal to 1, what happens actually? So here if you see, so when we switch theta is equal to 1, so what happens? So this implicit term will be fully vanishing. So there is no implicit method. Okay, so therefore this will be fully explicit. Okay, so now here what is happening? So what we are seeing actually, so we have seen a generic 1D diffusion equation. So 1D unsteady diffusion equation. That 1D unsteady diffusion equation. So we have written a general form of the discretized equation actually. So here the time derivative term. So here it is common. Okay, but when we come to space derivative term, so this is called time derivative term and this is called space derivative term. So when we are discretizing the space derivative term, so what is happening actually? So we have taken a switching factor called theta. So we use the switching factor called theta. So that switching factor theta will actually switches between the schemes, which is explicit and implicit. So when we take this as explicit, so when we multiply it with as theta, so when theta is equal to 1, what happens actually? So this will be a fully implicit. Okay, so when theta is equal to 1, this will be a fully implicit method. So when theta is equal to half, that will be semi-implicit method. When theta is equal to 0, so that will be fully implicit method. So these things actually are used for different applications of CFD. So let us take an example of 1D heat conduction. We can take 1D heat conduction equation, so which is of dou T by dou T is equal to alpha dou square T by dou x square. Okay, so the other application for heat transfer. So here we can use the same procedure for the other application of heat transfer. Let's see once again. So dou T by dou T, so which is equal to alpha into dou square T by dou x square. Okay, so this is what we have. Next, so we need to apply boundary condition. So let us take this as x is equal to 0 and this is x is equal to L. Okay, so let us apply the same technique, the semi-implicit technique and switching factor for this thing, for the heat transfer. Okay, so let us take, so T of I to the power of n plus 1. So previously what we have, the velocity variable u. Okay, so here we have temperature T minus T of I to the power of n divided by delta T. So here the capital T is nothing but its temperature. The small t is representing time. Okay, so is equal to, again we use the same switching factor, theta into, so alpha, so which comes as, so T of I plus 1 to the power of n minus T of 2T of I to the power of n plus T of I minus 1 to the power of n divided by delta x square. So this is the first term of the switching factor plus 1 minus theta. So T of I plus 1 to the power of n plus 1 minus 2T of I to the power of n plus 1 plus T of I minus to the power of n plus 1 divided by delta x square. Okay, so when you compare the previous equation, so here we can see, so here what do we have? So the same thing. So here it is 1D unsteady diffusion equation for the flow convection process. So here you can see this is 1D heat diffusion equation. So whatever equation you take, so basically the temperature or the convection equation, from in point of momentum. So these switching factors will not vary. So it is same, and the concept of the semi-implicit and fully implicit is same. So basically we apply these semi-implicit scheme, fully implicit scheme, fully explicit scheme with switching factor for energy equation, for momentum equation. So when we have the flow as incompressible, So when the flow is incompressible, what happens actually? We use continuity and momentum. Okay. So when the flow is compressible, so we use additionally we use energy also. Okay. So basically what is happening actually, so the temperature equation, so in order to use the semi-implicit scheme and the fully implicit scheme, or a fully explicit scheme with using switching factor, so we need to have the flow which is compressible, or we need to have the heat transfer phenomena. Okay. So with this we have seen the basic aspects of the semi-implicit scheme. So the next class we'll be seeing what is ADI. So basically ADI is nothing but so the alternating direction implicit scheme. So alternating direction implicit scheme in the sense, so along x direction, so we will have one method, in the y direction we'll have other method. So example, so here we have taken only 1D. So what happens in the 2D, so we have to see actually. So dou square, sorry, so dou t by dou t, which is equal to alpha into, so dou square t by dou x square plus dou square t by dou y square. Okay. So this is what, so basically this is 2D unstudied. So previously what we have seen, so we have seen, so dou t by dou t is equal to alpha into dou square t by dou x square. So basically this is what 1D unstudied. Okay. So for this we have applied semi-implicit scheme directly. Now so when we have this 2D unstudied equation, so how do we apply that semi-implicit technique? Okay. So what switching factors we have? So what is ADI? So basically we need to use that ADI method, so which is alternating direction implicit scheme. So what is that alternating direction implicit scheme? So we'll be seeing in the next lecture. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.